Alright, we're going to discuss the first of our case studies where it's going to be a little bit more on you to be able to put everything together. The tuning of the controller, the design of the controller, and the initial studies with the FOPDT constants to simplify the process. So go ahead, we'll discuss this liquid level control case. Our case study has us automatically maintaining a liquid level in the lower of two gradually drained tanks. And so we're going to be using adjusting the PID tuning. I believe we'll just be using a PI controller actually. So our first step, I've actually already gone ahead and done this. And I'll go ahead, I realized, go to view. We'll clear the output so we can run it all together. So for our gravity drain problem, we'll use graphical methods to obtain FOPDT model and report the values of those three parameters. So we'll just do a step test, and then we'll look at those FOPDT parameters graphically. So the way we'll do this is first let's go ahead. We're just going to set the parameters first. So we have the heights of our two tanks, and so the first index will be the first tank, second index of the second tank right here. We have the final time, and then a lin space to set an array all the way to that final time. Then we have a pump value, which is going to be our manipulated variable. And so it's going to be zeros, and then from 10 to the end, we're going to step it up to 0.2. So and then this valve setting, if it's 0, it's going to go direct to the top tank. 1 is go to the bottom tank. So we're going to go ahead and let it go to the top tank with that valve equal to 0. And then we're going to go ahead and record the solution in this H array, where we'll set the initial to H0 as well. So we'll go ahead, and how we'll do this is we'll just do a loop and loop through all the times, like with ODE 45, like we've done before. Let's briefly scroll down and let's look at our tank function. Objective, simulate model. Here we go, simulated model. Nope, that's simulate model. Here we go, here's the tank. So our tank is going to take a couple arguments. As always, we have our time in the first slot, in the first index of our arguments for the tank function, but we don't need it, so we'll put tilde. Then we have levels, which is the height that the tanks are filled. That can be, it's going to be unpacked here, but because it's our integrating element, it's going to be the second element. And the last two are arguments for pump and valve. We have two C's, which are our coefficients, one for the first tank and one for the second. And then we have two differential height values, and they depend on the height within your respective. Well, let's look at them. The first tank is the valve coefficient times 1 minus valve. So if valve is equal to 1, this will all be canceled out, times pump, and that pump value is that normalized value 0 to 1. And then minus, this is how fast it's going to the second one, C2 times the square root of height. The second one, we have the differential value of what's coming in from the first one, and that's plus that C2 square root of H1 that we have right here. And minus, we have C2 square root H2 as it drains out the bottom. And then we have C1 times valve times pump. And because if pump is equal to 1, it goes into the bottom tank. That's that value right here. If pump is equal to, or if valve is equal to 0, it goes into the top tank. And so that would be 0 right here, and that would all cancel out. Then we need to just think, if we have this, if we have a big pot, if we have a tank, and it reaches the full height, here our full height is 1, it can't go any higher. And so that's what we do right here. We say that if the height is greater than 1, and dHdt1 is greater than 0, dHdt1 is equal to 0. So the height is not changing anymore, is basically what we're saying. And then we'll return the differential height. So we'll go ahead, we simulate this tank step by putting in our inputs, simulating with ODE 45, and recording the result, and then setting the initial condition for the next loop, or the next iteration of the loop. So we'll go ahead and we'll run this section. And we can see with a 0.2 step in our manipulated variable, we go up about 0.16. So our gain is going to be about, like 0.16 divided by 0.2. About, I don't know, it's so hard for me. About 8. 0.8. Oof. So we have our process gain constant of 0.16 divided by 0.2. And so that's going to be, let's actually just add another, let's go like this. We're just going to take this right here, hit enter. Live editor, we're going to make a new section. There we go, section break. We're just going to have some code here. I like just doing everything. That way I can see it, and that way I can use it. So our tau, which is a process time constant, the tau p actually, because that's what we do. And you can see it's where we get 63% of the way to 62 to 63% of the way there to our final result. That's going to be about right. Actually, let's just do this. Our end is going to be 0.16, so 0.16 divided by, or times, 0.62. And we'll go ahead and we'll run this cell. So where we get 0.099, so right about here. And that's at about, let's say, 45. So tau p is equal to 45. No, 0.45. And then our dead time, we'll say that's equal to 0. It doesn't look like much. So we'll say 0.1, just so it's not an actual 0. Okay, now we're going to optimize it. To do that, we create our arrays again. We have our yp here, which is our process. Right? yp0 is the initial state. dt is the time difference between each time step. dy similarly is the second row, and it's the very end. So we're calculating our dy. Right here's our du, and so we're calculating our gain. Our tau here we guess is 30. Theta we guess is just 2 seconds, just something. And then you see right here, actually, we plug in some different guesses. Let's go ahead and plug in our guesses. So that's kp, tau p, theta p. We're going to go ahead and use fmin search to minimize our objective function. You'll notice you already have your objective function, FOPDT, and sim model. The objective function, as we've done before, will minimize the objective function, changing the value of x, where the values of x are kp, tau p, and theta p. It'll also give the values of the pump and the time points, so it'll be able to simulate it and find the constants that fit the best. Alright, so we have our optimized constants now, and I put this underscore OP just so that we can distinguish them. You'll notice that our gain is very close. Our tau, as it was 30, not 40, and it does a very good job of showing that. And our theta is about 3 seconds. So it wasn't 0, but it was close on the scale of 200 seconds. And so there's in yellow is our initial fit. Here, let me make it a little bit bigger. In yellow is the initial fit with our guesses, and this dashed red line is our optimized fit. So it's a pretty good fit. Simulates the system pretty well. So now we're going to repeat this, except now it's going to be with a doublet test. A doublet's where we're going to go, rather than just one change, we're going to change back as well, or change to a separate value yet again. So we're going to go ahead. There's a couple ways to create a PID controller. Repeat the test using a doublet test instead of a step test, and we're going to fit FOPDT parameters. So we're not going to do the PID controller. So instead, we have these values we're going to go through. We have our gain, integral parameter, and derivative. We have our set points. Here we change it a couple times. And then we have values to store the pump, time final, time initial, and the height initial like we had before. We'll go ahead and we'll see how this works in this section. So using these constants, we see we go up, we go down, we go up. It fits pretty well. Now if we were to do it a little bit more, we could optimize this as well. And that's what you do. You'd use a similar process from there. We'll leave that as something for you to figure out, just to practice figuring it out on your own. But it's the same cookie cutter process. We initialize our constants, we initialize the arrays, and then we fit them in. We fit them basically right here into just the same variables even. Let's move on now to the PID controller. So for the PID controller, we have our 3 constants we've used, we solve for. We also have our controller constants, so tau c, kc, tau I, and tau d. We've got these from the IMC tuning constants, or the ITIE tuning constants. Either way, it's just plug it in. We have our TS, which is our time plus 1. We're getting our lens space. Like before, we're going to set our set points. We're going to set the initial values for our pump, for our bias, our integral of error, and integral of absolute error, as well as our height. And we're going to go ahead and loop through the process. That will look like this. We'll first simulate the process by getting the integral of absolute error. We're going to then simulate the next step. We're going to record the result, reset the initial condition to the end of that, and use our PID controller to calculate the next value of the heater. That PID controller will set the value for pump I plus 1, as well as P, integral of error, and D. So you'll notice we did a nifty thing here where we already assigned that value for the next step. Finally, we'll go ahead and plot it. So you can see here, let's look at our results. And we could comment on these. I'll leave those questions. Actually, we'll discuss them in just a sec. You'll notice we have a little bit of oscillation. We also have a little bit of persistent offset. If I were to tune this more, what I would do is I would tune down the KC a little bit and tune up the tau I. By tune up, I mean tune down. But we want a little bit more integral control to drive this toward the actual set point, rather than being content with that persistent offset. So we have our criteria as far as how well we did, and there's a couple criteria that we're asked to comment on. The first is rise time, and we do a pretty good job of rising up initially, but then we need to get to the actual point. We have peak time, and that's the time it takes not to get to the point, but to get to that very peak. This right here, for example. Again, that's pretty fast. Overshoot ratio, we don't have much overshoot. In fact, we don't overshoot at all. We touch it once. We never overshoot. So maybe our KC needs to be higher. A damping ratio, that's the ratio that we have of these oscillations. And then our settling time is how fast we go from that peak to where we're settled and we don't see the oscillations anymore. So we'll briefly, just for fun, we'll take our tau p and we'll say minus 0, minus 0.3, and we'll run it again. Oh, it's tau c is what I wanted to do. So let's go back to the tau p, because that's not going to change much. It's not going to be 29 in a bit. So right here, tau c, kc, tau I, and our tau d is going to be 0. So our tau c, we have our kc, we have our tau p, and we'll just take off the semicolons. Scroll down and see what the output looks like. So we see that. Let's go ahead and so our tau c, what's our tau I? It's 30. That's our initial kind of heuristic, is just that they'd be equal. So we'll say minus 5. I have a little bit more integral control because it's on the denominator. So, and we accidentally ran the whole thing. Well, should be quick. Alright, here's our performance. Still not quite as good as I'd hope. So we're going to go ahead, KC, tau I. We'll just see right here, you can see these. We'll go ahead and just tune it down a little bit more. These are the constants from the TC lab. So I'll just leave them so it's not confusing. So let's say minus 15. Let's turn up the KC slightly, plus 2. Might be too much. Go ahead, run this section again. So we've got some more oscillation that will happen when our gain is higher, but we do move closer to our set point. So let's do minus 20 on our integral control. Drive in the right direction. Minus 25, do we dare? That's some instability there. Let's turn down our KC first. One section. Still unstable, so we'll say minus 23. That might be as good as we get. Let's just turn this up just slightly, so plus 1. I like that. So we do have some oscillation, which isn't the best thing, but we're right on that set point, which is what we want, our set points to get there. So there you go. There we have it. The main things to take away from this are, first, how to create a control loop from scratch and being able to do it on your own, thinking through the process of taking a measurement, measuring what the error is, using ODE45 to simulate the next step, storing the step and implementing it with your PID controller to get the output for the next manipulated variable setting. So there you go. Let me know if you have any questions.